We're going to talk about the fundamental theorem of calculus. And as you might be able to guess, this is really, really important, just based on the name, the fundamental theorem. We actually abbreviate it FTC usually just because it's really long and we talk about it a lot in calculus classes. So the fundamental theorem is important because it shows the relationship between derivatives and integrals. And you might be able to kind of imagine what the relationship is. I think we've talked about it a few times. Basically, derivatives and integrals are inverses of each other. So I'll give you the first part of the fundamental theorem. There's two parts to it. And then I'll explain what is really important in it and what it's actually saying. So this is the first part of the fundamental theorem of calculus. And I remember looking at this as a student and I really had no idea what was going on with it. It's kind of, there's a lot going on with this theorem. They give you way too many things to really understand it by just looking at it. So they tell you that if f is a continuous function, then the function g defined by this thing, which I'll write, I'm going to put a box around over an interval, is continuous on that interval and differentiable. This is the really important part, and that is that if you take the derivative of the integral, you get what's inside of the integral. So that's the important part, is the stuff that I just outlined in pink. Yes, for pretty much to do most stuff in calculus, you need a continuous function, you need a differentiable function. Those things are really important. I think because the parts with the continuous and differentiable have so many words, people get kind of bogged down by them. But the key thing I want you to notice from this is that if you take the derivative of an integral, you get what's inside the integral. So integrals and derivatives are inverses. That's what this is telling us. So we're going to do two examples, and you might be looking at these examples thinking, wow, that looks really hard. But believe it or not, I think these are the two easiest examples we're going to do in the entire class. And by entire class, I mean like the entire 9 months of the school year. So we are finding the derivative of that integral. So for the first one, to find h prime of x, we are taking the derivative of that integral. If you want, you can, but you certainly don't have to, you can write it like this. So you got to remember that when you take a derivative of an integral, you get what's on the inside. The only thing I think that might throw people off is that we're taking the derivative with respect to x, so our final answer has an x, but actually it's just going to be what is inside of that integral. So that's my answer. You don't actually have to do any math. I think the number one mistake I see on this, and it's kind of a tragic mistake because people spend a lot of time doing this, is people try to take either they try to take the integral of what's inside there, or they try to take the derivative of what's inside there. It takes a long time, but actually you don't need to do any work on this. You just need to pretty much rewrite the function on the inside of the integral with the variable x. Number two is the same idea. I am going to say the thing at the bottom does need to be a constant in order to work these problems out. If you have a constant, the derivative of a constant actually goes away, so it's not going to be a part of the problem. I will show you an example later on, like why this is going to work, but we need the second part of the fundamental theorem for me to show it to you. So the answer for this one is just going to be this right here. So please don't overthink these. That's all we're doing. So we're going to do one more example. And I want you to notice that in examples 1 and 2, my upper bound of my integral was just x. In this one, however, my upper bound is actually a function of x. So we're going to take the derivative, same as what we were doing before. So we're taking the derivative with respect to x of this entire function. And the big thing in this one is that with an upper bound that's not x, we need to use the chain rule. So there's two things that we're going to do. The first thing is that we are going to replace that t that's inside of our secant with an x to the fifth. It's a 5, by the way, not a 3. The second thing that we need to do is, since we took a derivative and we had something on the inside of the derivative, we need to use the chain rule. So when I use the chain rule, that means I need to take a derivative of that x to the fifth. That's going to give me 5x to the fourth. And this actually is my answer. You can write it out like this if you want to. But keep in mind that you do need to use a chain rule for this type of problem. So let's go ahead and we'll talk about the second fundamental theorem of calculus. And you're going to be using this all the time. It's going to come up a lot. It's really important. And this actually is going to help us evaluate definite integrals. I don't know if you realize this or if you noticed this in the last section, but we had a lot of definite integrals, meaning we had like an upper and lower bounds, but we only evaluated them by using geometry, by finding the area under the curve. So we will learn a faster way to do it. I want to make sure that you understand the difference between a definite and an indefinite integral. So a definite integral is going to be, those are the ones where you see like an upper and lower value. The answer for a definite integral is going to be a constant, and it represents area. So now, an indefinite integral, those ones are the ones where you do not have the upper and lower values. You just have like something like this. The answers for those are going to be a function. And if you remember, when we did those ones all had a plus c, because there were lots of different indefinite integrals. So there would be many, many, many possible answers, an infinite number, because of that plus a constant. Definite integrals don't have a constant of integration because the answer is a set number. It is the area under a curve. So part 2 of the fundamental theorem of calculus is going to be used a lot. It shows us how to evaluate definite integrals. It's a lot faster than using Riemann sums. It's a lot faster than finding the area under the curve using geometry. So what we're going to do is we're going to look at our function, take the antiderivative, and then we're going to evaluate it at those two upper and lower values and then subtract them. So let's go ahead and do some examples. So for my first example, I am evaluating the integral of 3x squared dx from 1 to 4. You are welcome to pull that 3 out front if it makes the problem easier for you, but I just assume not bother. So I'm going to put the 3 there. Now, in order to evaluate this, I am going to find the antiderivative of x squared. And the antiderivative of x squared is x to the third over 3. You'll notice that I nicely gave you something where the thing on the bottom cancels out. You're not usually going to get something that nice. So the way that I'm going to show that I'm going to be evaluating this from 1 to 4 is I usually draw a line next to it. That's generally what you're going to see. Sometimes you'll see like a bracket like this. I prefer the line. I don't really care which of the two you do. So then I am going to write it from 1 to 4. And actually, I'm going to cancel out those 3's before I go on. So my answer is going to be from 1 to it's going to be x to the third evaluated from 1 to 4. So the first thing I do is my upper value, which is 4 to the third, and then I do that minus my lower value, which is 1 to the third. I get 64 minus 1, which is 63. So you're welcome to go ahead and try these on your own, but either way, if you do that, go ahead, pause, and try the problems. So for number 5, we are finding the definite integral of e to the x plus x from 0 to 2. The antiderivative of e to the x is just e to the x. The antiderivative of x is x squared over 2. Remember, you're adding 1 to the exponent and then putting that over the new exponent. That's going to be evaluated from 0 to 2. So I first am going to get, when I evaluate it at 2, I get e squared plus 2 squared over 2. Then I get minus e to the 0 plus 0 squared over 2. And e to the second, I would recommend not trying to evaluate that. I think it's better just to leave that as e squared. Then I get plus 4 over 2, which is 2. Minus, this is going to be, this is equal to 1, this is equal to 0, so it's going to be minus 1. So my final answer for this one is just e squared plus 1. So now you might be looking at 6 and probably 7 too, and wondering what function are we looking at here. So actually, for number 6, this is just another way to write 1 over x times dx. And I think oftentimes when students first see these, the first inclination is to do like x to the negative 1 and then try to add 1 to the exponent. Then you would get x to 0. That's not what we're doing. If you remember, if you have 1 over x, in order to take a derivative of something, you get 1 over x, you actually, your antiderivative is actually going to be ln of x. And we are going to write that x with absolute value bars around it. So just be careful about that type of thing. Even though you have a something that's to a power, you're not going to use the power rule for integrals. So that's going to be evaluated from 3 to 6. And I'm just going to get ln of 6. It's totally fine if you take the absolute value bars out when you if you don't have a negative, minus ln of 3. This answer would be perfectly acceptable if you were on a free response question. However, if you were doing a multiple choice, you would be expected to know that this is the same as ln of 6 divided by 3, which is the natural log of 2. So then for number 7, there's 2 things going on. The first thing you might be thinking, like, why don't we have a function there? There actually is a function. You can think that there's an invisible 1 in front of there. The second thing I want you to remember is that if your limits of integration are out of order, you need to make it negative and then switch the order of them. So I have 1 times dx. The antiderivative of 1 is actually just going to be x. And you can either keep that negative on the outside of the parentheses and add it later, or you can work out the problem with that negative there. It doesn't matter to me which of the two you do whatever's easier for you. So my first term, when I evaluate negative x at 3, I get negative 3. And then my second thing, I end up getting a minus 1 in my parentheses. This gets confusing because there's a lot of negatives, so just be really careful. I'm hoping I didn't make a mistake here because it's very, very, very easy to mix something up. And my answer for this one should just be negative 4.